This is going to be an introduction to relational databases, specifically what makes a relational database a relational database. Because at CANA, we're a data analytics company. So we deal with a lot of data. That data, we tend to get the data and then run modeling and simulation on it. We don't manage a lot of data, but as we move into some new projects, like IMAT and Alaska Hero, we're using relational databases. Behind Appian is a relational database, and then the new Alaska Hero project looks like we're going to use a relational database. So I'm going to walk you through a relational database example, and then I'm going to talk about some best practices we can use at CANA. I'm going to start off by answering a question: what is the most popular database? And that would literally be Excel. Excel has rows and columns in a tabular format for managing data, and we use it all the time for database tables like CSV files. One of the things, though, is Excel isn't relational. And when a database isn't relational, it usually means it's not normalized data, which means that business data is repeated unnecessarily, or in a relational database, you don't need to repeat the data, which I'll take you through in a moment. If you have a bunch of data and you can use what's called CRUD, create, read, update, and delete that data, then you have yourself a database. That's the basics of what we use a database for. We just say CRUD, right? It gives you all the access to the data that you need. There's some more technical properties when we're executing transactions with a database, and these are known as ACID properties, standing for atomic, consistent, isolation, also known as independent, and durable. And what that means is when we send a transaction to a database, that transaction is atomic in that either the entire transaction succeeds or everything rolls back. But part of the transaction won't succeed and part won't fail. It's either all or nothing. So it's atomic. And this helps move the database from one consistent state to the next. These transactions that we send to the database are done in isolation, or they're done independent of one another. One transaction doesn't know about the other until it's been completely committed to the database. And that ends up giving us a database that's durable. And by durable, we mean that if we lose power while we're writing to the database, we don't corrupt the data in the database. And the way that generally works is that the data before it's written to the database, after you send it, has a little in-between step where it might write the data to what's known as a write-ahead log. And then from the write-ahead log, the data is written to the database. So if at some point the database fails, when the database starts up, it can compare the database to the write-ahead log and figure out if there are any discrepancies it needs to resolve. So a database will stay intact if it's a good database, with the exception if a hard drive fails, right? Your data is lost, but that's beyond what a database can control. Here's a definition of a relational database. This is one of those times where Wikipedia kind of lets you down. If you look up what a relational database is in Wikipedia, it talks about the relational model, and it uses very technical terms like first order predicate logic, and I really don't know what that means. So I've simplified that to this definition here. A relational database is a digital data collection for managing tabular data using a structure and language. That part that's in bold is what Excel does very well, right? It manages tabular data. What Excel doesn't do is it doesn't have structure and it doesn't have language. And by structure, we're talking about a database schema, sometimes known as an entity relationship model. And then we have a language that we communicate with databases. Most popular one is SQL, sometimes called SQL, which stands for Structured Query Language. I'm going to walk through an example of taking a denormalized database and normalizing it into a relational database. When we use terms like normalized or denormalized, normalized simply means we're not repeating business data unnecessarily. So here's a database. It has one table, and we're looking at movies that were made by these two directors, Steven Spielberg and Penny Marshall. I'm sure we all know who Steven Spielberg was, and for those of us that are older, Penny Marshall rose to fame on the show Laverne and Shirley back in the 70s. If you look at this database table, you'll notice that the names are repeated in multiple rows. And these addresses I'm using are hypothetical addresses, and I'm saying that this is the address where the director lived when a certain movie was released, because the Academy Awards need to know where to send the invite to the Oscars. So we need the person's home address. And you can see the names and addresses are repeated. So this is denormalized. I'm going to show you how we break it down and normalize the data into a relational database. This is what the structure of a database looks like in my example. This is the entity relationship model, or the schema. This doesn't show you the data in the database. It shows you how that data is modeled, though. We have a database table name. For example, there on the left, we have director, and then we have a list of column headings, in this case, name and primary key. And those arrows tell you how tables relate to one another. When you look at this, if you follow the arrow from director to movie, the two arrowheads on one end are read as many, and the one means one. Reading the director relationship to movie, a director can direct many movies. But going back the other way, a movie is directed by one and only one director. And by pushing data out like this and relating it, we don't need to repeat it. Here's an example of what the director table would look like in this relational database. We have two rows, and row one with a primary key of 1 is Steven Spielberg. Row 2 is Penny Marshall. And a primary key is just a way to identify or unique a row in a database table. It's the exact equivalent of the integers we see for the rows in Excel. And each number uniques that database row so you can get to it. It's an artifact of the database. Now we're going to take a look at the address table in the upper right. And this is an example of the data that's denormalized in the address table. Again, we have the primary keys and then we have the full address. For right now, just ignore what the foreign key is, and I'll tie that all in just a bit. And then we're going to look at the movie table here on the bottom right. And this is what the movie table would look like. We have each movie. It's listed once and only once with a primary key and a foreign key. And now I'm going to tie all that together. Here's the director, the address, and the movie database tables. If we look at the movie table in the bottom right, what the foreign key does is it tells you what the primary key is of the table it's related to. So the second column here, which is the movie director foreign key, for the first 3 rows, we see a 1. So if you wanted to know who directed Close Encounters of the Third Kind, you look at the director foreign key and it says 1. If we go up to the director table, we see next to 1 primary key is Steven Spielberg. And the same applies with Penny Marshall. This looks more complex. It's less human readable than a flat file, but it makes the cost of change minimal. For example, if Steven Spielberg married Penny Marshall, let's say Penny Marshall took Steven Spielberg's last name, now she's Penny Spielberg. We only need to go to the director table and update the second row in the director table from Penny Marshall to Penny Spielberg. And that's the only change you would need to make. If you went to the movie table and looked at row 6, A League of Their Own, if you wanted to know who directed that, you would follow the foreign key 2 to the primary key 2 in director table, and the name would be Penny Spielberg. That's why we relate database tables. Going back to the original flat file, if we wanted to change Penny Marshall's name to Penny Spielberg, we would have to do a complete table scan, find all the cases where it used to say Penny Marshall, and change it to Penny Spielberg. That's not a big deal when you have 6 rows. But consider a website like Twitter, where 500 million tweets are sent a day. That's literally 6,000 tweets a second that are sent by Twitter. A user on Twitter can change their username to any other available username at any time. Because they use a relational database, that username only needs to be changed in one place, and all the other tweets that relate to that user will be updated when they follow that relationship. I mentioned that the schema part here, this is the schema. Now I'm just going to show an example of what SQL looks like, or the structured query language. I'm sure a lot of you have seen this. This is a sample SQL statement that if we executed it against the relational database I showed earlier, it would return a list of all the movies that Penny Marshall made. And in this SQL statement, we join 2 tables. That's what a join is. It means, hey, we have a relationship based on a primary key and a foreign key, and following that relationship or making that join in SQL code, we'll get back the data we want. This is, a little verbose. Other languages have ways of generating this automatically. I'll just give one example here of Java. Here's 2 lines of code that do the same thing. And the first line in this Java code creates, an object called Penny Marshall. And it's basically going to the director database table and returning the row where the name is Penny Marshall. And then we just ask the Penny Marshall object for all its movies. Now, what Java here is doing behind the scenes is it's dynamically creating the SQL that we see above to get this information. But since it's a higher level language, it's easier to code it without having to worry about the SQL. Now I'm going to talk about some 5 basic database rules that we're going to follow as a best practice here when dealing with relational databases at CANA. The first one is primary keys. A primary key should be an integer, just a positive integer, and you never want to build any intelligence or business logic into your primary key. It's simply an artifact of the database. For example, you don't want to use a person's social security number as a primary key to identify a person. And that's not for privacy reasons, that's more for practical reasons. It is entirely possible to have multiple people with the same social security number. And at some point in the future, we're probably going to have to recycle social security numbers, because there will be more people alive or who have lived in the US than we have a numbering space for social security numbers. So simply don't build any intelligence into a primary key. That way, if you ever have to migrate a database from one database type to another, you don't have to worry about what the primary keys represent if the new database system uses some different type of primary key algorithm. Table names, when you name tables in a database, the name of the tables almost always should be singular, right? Because you're identifying what a single row in a database table represents. So if you have a list of employees, the database table for that should be employee. Lookup tables are just simple tables that you put data into that doesn't change very often. For example, states. If you're creating an e-commerce website and you want to ship to all 50 states, you create a database table that has 50 rows in it. And then you realize, oh, I forgot Washington, D.C. So you just add that to the states database table. And the next time the application starts up, it just reads those 51 rows now. And that's what it will use to populate the state you're going to ship a product to. And then if you expand to say Guam, you just add another row. The beauty is you're making a change in one place, the database, without having to change any code, recompile it, and then redeploy it. Primary keys in tables. A database table should have one and only one primary key, with the exception of a table that's joining two tables in a many-to-many relationship. Generally, your relationships should be one-to-many to properly normalize data, but sometimes two tables need to have a many-to-many relationship. And an example might be a database table that keeps track of parents and a database table that keeps track of children. Parents can have multiple children. Children obviously have multiple parents. In that case, what you do is you take the primary key from each of those tables and you propagate them into a little in-between table that only has two values, and it's the two primary keys from the other table. So what you're doing is you're propagating foreign keys and using both of them as primary keys in a database table. I can't think of any case where you would ever want more than two primary keys in a database table. And last but not least, this leads to a pet peeve of mine. When you're storing data in a database, relational database, you define what type of data you're storing in each column. Is it a string? Is it a number? Is it a timestamp? Generally, if you're not going to use the data for any type of calculation, you should probably store it as a string, what a lot of databases call a varchar, which means a variable character length. It's the same exact thing as a string. A very good example of what you don't want to do is you don't want to store things like an NSN or a social security number or a credit card number as a number. And I saw this on a website once where I went to check out and I put in my 3-digit code for my credit card security code, and my number was something like 072, and it kept saying it failed. And I reached out to the database administrator because I figured out what he had done. What he had done was he had made that field a number, and the 0 in my 3-digit social security, in the 3-digit credit card security code had been truncated. We see that a lot of times if we export something like a social security number or maybe a NIN that begins with a 0 into a CSV file. We have to go out of our way to put quotes around it. Otherwise, the system will think it's a number. And we may have seen exponential columns with NSNs because Excel might think an NSN is a number, and it's such a long number, it represents it as something like 1.23 times 10 to the 16th or something like that. And this leads to another pet peeve of mine when I put in a phone number or a credit card number with spaces or dashes, and the website says, hey, this is the wrong format. It's a pet peeve of mine because it's not very hard for a software engineer to take whatever someone enters as a phone number and strip out anything except the characters 0 through 9. Relational databases are obviously one type of database, and the most popular relational databases are Oracle, MySQL, PostgreSQL, SQLite. Those are very popular relational databases, but there are completely other types of databases. The most popular one here that I circled in the red is a NoSQL database. And as the name suggests, you don't use SQL, but the big strength of a NoSQL database is that it's good for millions and millions of rows of data stretched across multiple databases. So a NoSQL database basically is not a relational database, but it allows very, very fast lookups of data when you have millions and millions of rows. And here's a link to the 5 best practices for relational databases that I went through earlier. And with that, I'll take any questions.